Welcome back to the channel and to our stupid simple small engine fuel injection project. So right away, I want to make sure that folks understand that stupid simple means we're going to ignore pretty much all the rules that pertain to how fuel injection is supposed to work. And our goal is to get this 212cc Predator to run on just one sensor, which is the map sensor. And of course, some simple code on the Arduino. So there are plenty of folks in the audience who know this is difficult, if not impossible. You see, I have a very smart audience, which I'm thankful for. Anyway, I'm very much aware of what it actually takes to properly do fuel injection, and this video is called Stupid Simple Fuel Injection for a reason. I covered my stupid simple plan in the previous video, and if you haven't seen that yet, I recommend you watch it before getting up on the soapbox and start pontificating all the rules. Rules are for the smart people, and this is called stupid simple for a reason. Right now, we only have one sensor, which is the map sensor, and that's all, nothing else. So the plan is to build a continuous fuel injection system that operates similar to the original Bosch CIS system that was used on European cars back in the early to mid 70s. The Bosch CIS was a purely mechanical system. However, we're going to improvise and mimic the CIS system with modern electronics. In order to make the system as simple as possible, we're also going to mimic the throttle body injection that was used on GM vehicles in the 80s. My rust-free and perfectly normal Chevy S10 pickup, which should not be confused with the one-of-a-kind 1.6-liter Volkswagen diesel-powered S10 pickup. Nope, these are two completely different trucks. Anyway, this normal Chevy is equipped with a 4.3-liter gasoline V6 with throttle body fuel injection. As you can see, this sort of fuel injection is a bit crude, and it just drizzles gasoline old-fashioned style into the cast-iron V6 engine. It works, and keep in mind the entire fuel injection system on this truck from the fuel tank to the throttle body was rebuilt, and this is as good as it gets. The sloppy way the injectors spray fuel is completely normal. On the Predator engine, we have our injector mounted before the throttle body, just like on the Chevy. Now, disregard the carburetor. Yeah, this engine does have a carburetor, but there's no gasoline in it. We're using the carburetor as a throttle body and nothing more. Now, later in the video, we'll make some massive changes to this setup, but right now this is exactly where we left off in the previous video. Now, homemade electronic fuel injection for small engines is a fascinating topic, and we had great numbers on the previous video. So, we're going to take this step by step, and this system will evolve, but keeping it stupid simple is our primary goal. Before we jump into the testing in today's video, I want to give a quick explanation of how we're using the Arduino and the challenges we're facing by only using one sensor, which is the map sensor. If you recall from the previous video, we connected a vacuum gauge to the intake manifold on the Predator engine. The map sensor is also connected to the intake manifold. Now, the amount of vacuum in the manifold is directly proportional to the load on the engine, and we really need to know exactly how much vacuum is in the manifold. And that's sort of a problem. You see, when the engine's running, the vacuum in the manifold is not stable, and that's because it's a one-cylinder engine, and the intake manifold only sees a brief period of vacuum every other rotation of the crankshaft. And that translates to the vacuum gauge going nuts. Well, it's not just the vacuum gauge that's going crazy, it's the map sensor too. My initial response to this problem was to put a restriction in the vacuum line to slow down the vacuum signal, but that resulted in a very low average vacuum signal. And if we look at a snapshot of the gauge, we can see the actual vacuum signal is much higher for a split second. The problem is, we really need to know what the actual vacuum is, but the gauge and the map sensor show the vacuum is pretty much everywhere all the time. Now, if we had a crank position sensor, we could use that to trigger the Arduino to sample the intake manifold pressure at a certain point during the intake stroke. But as you know, we don't have a crank position sensor yet. Without the crank sensor, our only option is to use brute force to get an accurate reading of the manifold pressure. So, as stupid as this sounds, I wrote a bit of code that sampled the map sensor 3,000 times, and it compared each sample to the previous sample, and if the new sample had a lower number, then it would update the value. Anyway, after 3,000 random samples of the map sensor data, I was able to get an accurate reading of the manifold vacuum. Now on a map sensor, the lower the number we get translates to higher vacuum. so we're always looking for the lowest number. Anyway, electronics and software operate much faster than the silly mechanical systems of a gasoline engine, and using this brute force method to obtain map sensor data is not too extreme. It's definitely stupid, but without a crank position sensor, this is our only option today. So we're going to roll with it. Now, just to be clear, I didn't do 3,000 samples in a row. Nope. You see, I grabbed a sample from the map sensor on every loop of the program, and after 3,000 loops, that's when I had the code spit out the lowest number it could find. It took a little bit longer than a blink of an eye to get this data, but all in all, it was the best way I could get what I wanted. My attitude is this: I don't care if the computer has to work overtime. Meh, that's not my problem. Just give me the data I want now. So today we're going to take this project to the next level, and we're going to be using this alternator to put a load on the engine, because in the previous video, all we were able to do was get the engine running with no load. Plus, in the previous video, we didn't use any of the data from the map sensor, and the engine was just running on hard code. Hard code worked, but without the data from the map sensor, this engine had no chance of running with a load on it. Remember, the map sensor measures the vacuum in the intake manifold, and the vacuum is directly proportional to the load on the engine. It gets a little fuzzy, but that's mostly true. Anyway, the modified alternator is controlled by this gizmo, which allows us to overdrive the output of the alternator so we can dump the energy into this garbage can full of water. Well, we're actually dumping the power into heater elements, and the water just keeps them cool. How all this works was covered in Season 6, Episode 5. The bottom line is, with this setup, we can put a decent load on the engine. Now, we did discover problems with the current fuel injection system in the previous video, so before we collect the necessary data to complete the software, we need to do a quick upgrade to the engine. Let's go to the bench, and I'll show you the new parts that we're going to install. So this is our spare engine, and I'm using this engine to design the parts that we need. The carburetor we're using is basically just a throttle body, and it doesn't provide any fuel to the engine. The main purpose of the carburetor is to retain the governor linkages. I reckon that we really don't need the whole carburetor, so I decided to modify an extra carburetor. Now this guy is pretty much the same carburetor, but it's been cut in half and all the empty space has been filled in with JB Weld epoxy. You know, this really wasn't necessary, but it provides us with a smaller throttle body with the correct attachment points for the governor linkage. For now, I want to retain the governor, so I have an automatic engine speed and load compensation. Having a working governor will help speed up the development process. Anyway, I went ahead and 3D printed a bunch of new parts, and the inside diameter of these new parts matched the smallest diameter of the carburetor venturi. This should actually help accelerate the air through the throttle body and help maintain some sort of fuel atomization. How good it'll be? Well, that's anybody's guess. So we start off with this Garolite heat shield, and this guy will isolate the hot cylinder head from the ASA plastic 3D printed parts. The ASA plastic can more or less handle the heat when the engine's running, but using this heat shield will prevent the heat from the cylinder head from soaking into the parts after the engine is shut off. Next comes the vacuum port for the map sensor. The inside diameter of this part was sized correctly, and this should help prevent a condition called wall wetting. Now, wall wetting is when raw gasoline attaches itself to the surface of the intake manifold, and it kind of screws up everything. Now, this vacuum port should be installed with the bung pointing up, but I screwed up and that interferes with the throttle linkages. So I'll print another one, but for today, we'll mount this thing upside down. Now, the reason we want it pointing up is to prevent any raw gasoline from reaching the map sensor via gravity. Next comes our custom throttle body with the correct attachment points for the governor linkage. And finally, we can slip on the injector housing. This part was redesigned slightly, and I forgot what I actually did to improve it, but I'm sure it was important. Now, throttle body injection will work, and we've proven that already. However, I do have a port fuel injection manifold that I'm working on. Unfortunately, this version gets in the way of the throttle linkage, so it needs to be redesigned again, and we'll get back to this idea sometime in the future. Let's install this stuff on the actual engine and see how it works. So I had a number of requests from the previous video from folks who wanted to download the software that I wrote. Now, I don't have a problem sharing my software, but if you paid attention to the previous video, the software didn't do anything. Sure, it ran the engine, but I had to manually adjust the duty cycle to control the amount of fuel being injected. The software basically had no value, and it wasn't capable of keeping the engine running with a variable load. It was basically just step one in the many steps we'll need to take in order to get this engine running decently. Oh, here's the difference in size for the vacuum port. The one on the left was huge, and it may have been what was causing the wall wetting situation. The newer red one has a smaller diameter hole, and this should help maintain the velocity of the airflow and has less surface area where raw fuel can land. Anyway, the software we'll develop today will still be bunk, and it isn't worth sharing. I think at this point in the project, we're 1 or 2 more versions away from something that actually works in all situations. We need to test what we have and then learn where we need to make improvements. Okay, that's it. The junk is installed and the governor linkage still works. Not too shabby. Oh, some folks noticed this coil pack just hanging out. Yep, this is an actual ignition system for this engine, and we covered this in Season 6, Episode 3. It works, and it uses a crankshaft sensor for the trigger. So the coil is nice, but we may have to repurpose the crank trigger temporarily for the fuel injection. We'll get back to this later. Well, this is all the stuff we have that controls the fuel injection. The Arduino that we're using is inside this handy enclosure, and this knob is how I manually adjust the duty cycle of the injector. And this red button is the primer button. All this stuff was covered in the previous video. Basically, what we have here right now is an Arduino toggling this transistor to fire the fuel injector at a fixed frequency. Now, adjusting this knob varies the duty cycle of how long this injector stays open and squirts fuel. A short duty cycle will allow the injector to squirt a tiny bit of fuel, and a long duty cycle will allow the injector to squirt a lot more fuel. Now, this is a continuous fuel injection system, and that means the fuel is constantly flowing at a fixed frequency. Right now, the frequency is at 25 times per second or 25 hertz, which is close to just willy-nilly. Remember, this is stupid simple. Despite it being a fixed frequency, it's the duty cycle that makes a difference of how much fuel that flows. And the point of this whole single sensor experiment is to see if we can get the map sensor to automatically adjust the duty cycle for an air-fuel ratio that's close enough. Anyway, in the previous video and at this moment, the map sensor is not doing anything. And I've been manually adjusting this knob to set the air-fuel ratio. Hopefully today we can bridge the code and the map sensor will do what we want it to do. Okay, a quick edit here. I forgot to mention that the Generous Motors map sensor was acting goofy, and it may be a bad sensor. Or perhaps raw gasoline got into this port and it's causing problems. Anyway, I didn't trust the data coming from the sensor, so I swapped in an MPX 4250. This is an extra sensor I had from my Speeduino NO2C system. This sensor can read both vacuum and positive pressure in the manifold. Perhaps this may not be ideal because the vacuum readings are low resolution, but on the other hand, the Speeduino NO2C uses this for single-cylinder engines, so maybe low-resolution vacuum data is good or gooder. It's hard to say. It doesn't matter because this is the only trustworthy sensor I have at the moment, and this is what I used. You can sort of see it right here, but for some reason I forgot to mention this while shooting the video. Anyway, let's fire up the engine and see if it'll run. Fuel pump on. Prime the engine with some raw gasoline. And it's running. I guess that's good. So this engine's running on the previous software, which is no good. Now, like I mentioned a little while ago, this software is nothing special and it relies on manually adjusting this knob in order to correct the air-fuel ratio. So yeah, the engine runs, but watch what happens when I goose the throttle without manually adjusting the air-fuel ratio. Yep, without the feedback from the map sensor, all the engine will do is idle. Goosing the throttle gives the engine more air, but the duty cycle for the fuel injector doesn't change. I kinda thought this was obvious in the previous video, but I think some people missed that fact. The next part of the video is very hard to capture and explain, so here's kind of a cartoon of how I'm going to collect the necessary data in order to finish writing the code. First of all, we'll get the engine running at full throttle, and to do this I have to increase the throttle while adjusting this knob to correct the air-fuel ratio. Once the engine's up to speed, then I'll capture the data from the laptop. Basically, I want to know the map sensor data and the duty cycle. In this case, range is the duty cycle, and disregard where it actually says duty cycle. That's just an artifact in the code. Oh, and the data is in counts, which is gibberish to some people. Anyway, once I record the data point for wide open throttle with no load, then I'll apply a light load to the engine using the load control box. And at the same time, I'll be adjusting the air-fuel ratio. And then I can grab data from the laptop. Of course, after that, I'll apply a medium load to the engine, grab the data, and finally apply the maximum load to the engine and grab the data. Each time the load changes, I obviously have to adjust the air-fuel ratio. This will give me 4 data points on how much fuel the engine wants at various loads. Now, the tuning of the engine at each load is done by ear, and the actual air-fuel ratio will be a mystery. Tuning by ear is perfectly fine if you understand how the engine should sound. Anyway, no worries, this sounds a bit crude, but in reality it's a great starting point for the information that I need. Fast forward a bit, and here I'm making the final load adjustment and adjusting the duty cycle of the injector, so the engine can carry the load smoothly. You know, it's a lot of back and forth to make all these adjustments by hand, and then capture the data and confirm the data. So let's take a look at the scoreboard. First of all, the data is in counts. You might expect to see this data in kilopascals or inches of mercury, but nope, it's in counts. And you might expect to see this data in percent, but once again, it's in counts. To me, the actual engineering units don't make a difference, and what I'm looking for is the ratio between map and duty cycle, because at that point it's just math. So when it comes to the map data, the lower the number means the higher the vacuum in the manifold. And if we look here, at idle we show 60 counts, but at wide open throttle with no load, we show 52 counts, which means we have higher vacuum at wide open throttle than we do at idle. That's a problem we need to deal with at some point. It's a bit of a paradox. However, from this point down, the numbers look good. At a light load, we get 100 on the map and 140 on the duty cycle. At medium load, we get 150 and 175, and at full load or heavy load, we get 193 and 206. Let's disregard the idle data for now, and with the rest of the data, we can work out a solution of some sort. Well, what started out as a good idea and a fun project started turning into more work than I wanted to do. Calculating formulas and testing them on the engine became a quagmire of complex math and disappointment. And that's when I turned to the dark side. I guess this is how the downfall of humanity begins. So, I'm not proud of this, but I asked ChatGPT for help. You know, I started off with just bouncing some formula ideas off Chat, and without telling Chat what I was up to, it figured out I was trying to write code for fuel injection. That's creepy. Once Chat figured out what I was trying to do, it had all kinds of suggestions, and it came up with some really good ideas. I tested a few of them, and some worked. Now, Chat didn't write the software, but it did write a snippet of code for the Arduino, and I laced that into my code. Well, it's not perfect, it actually works really well. I reckon if I gave Chat more data points, we could refine this idea. But no matter what the AI is capable of doing, I don't believe it could solve the illogical problem where we have higher vacuum at wide open throttle than we do at idle. That's too much of a paradox. However, I do believe it could solve the problem if we fed it RPM data. With RPM, we have a good chance of making this code perfect. But today we don't have RPM, and that's fine. Let's see how the snippet of code that Chat wrote works with our stupid simple system. Okay, we're all set to test the engine with the updated code. The paradox issue has not been solved, so we're going to cheat a little bit, and the idle function has been hard-coded for now. Now, anything above idle will rely on the map sensor for fuel injection feedback, so that means the duty cycle for the injector is now completely automatic. So now we're at full throttle with no load, and I don't have to fiddle with the knob anymore. Let's put a load on the engine and see what happens. it handles the load perfectly. This is actually really hard to do with simple code and only one sensor on the engine. So that, ladies and gentlemen, is continuous electronic throttle body fuel injection with only one sensor, and to be specific, we're only using a map sensor. But I cheated. You see, the fuel injection works, and it works really well at high speed. It'll carry a large load no problem, but we have some problems at idle, and I'm not sure the idle problem can be solved. So yeah, the engine will idle, but I repurposed the prime button to work as the idle button. Well, at least I'm being honest and I'm not hiding anything from you folks. Let's take this one step further just for fun. Fast forward a few minutes and I've updated the code to allow the engine run with automatic fuel control for idle. And as you can see, I no longer have to push the repurposed idle button for the engine to idle. The run switch is in the run position, and at this point the Arduino is doing full engine management with only one sensor. This is really sketchy because our data crosses over in an illogical fashion, but the chaos that's going on inside the Arduino seems not to be bad enough to keep the engine from running. This part of the video is mostly for amusement and so you can see how unstable things get by adding the data for idle. So after a few moments, we start getting hysteresis from the governor because we're at a point where the vacuum is bouncing back and forth and telling the Arduino that we need fuel and then nope, we don't need fuel. This happens very, very fast inside the computer and the calculated duty cycle for the injector gets a little bit wacky. Anyway, this is unacceptable even for the stupid simple fuel injection project. Now, for some reason, putting a load on the engine makes things worse. In theory, the load should put the calculations in a more stable zone, but that's apparently not the case. When I include the data for the idle, that makes the software unstable due to the paradox. And this issue cannot be solved if we continue using just one sensor. In order to get around this issue, we need to give the computer the RPM data. So at that point we would have two sensors, which is still not a lot. However, if we go with two sensors, why not ditch the map sensor and just use a throttle position sensor and RPM? And that will allow us to use alpha N tuning strategy. I think alpha N would be more stable, however there is a problem if we go down that road. You see, putting a throttle position sensor on one of these engines is not that hard, but the drag from the throttle position sensor would upset the way the governor works. If possible, I want to keep the governor. So alpha N is probably the way to go, but just for fun, let's keep the map sensor and add RPM to the mix and see where that takes us. Keep in mind, this is the stupid simple fuel injection project, and more parts we add, the less simple it'll get. Obviously more sensors would be better, but that's not our goal. So, I hate to admit it, but chat was a big help with today's video. Basically, chat suggested using a lookup table with interpolation. This snippet of code was a function call outside the main program loop. You know, chat also wrote a smoothing routine for the map sensor data. Now, I didn't ask it to do this because my brute force method was deemed adequate. However, since chat figured out I was doing fuel injection stuff, it suggested this feature and I was like, well, okay. With chat's little snippet, I was able to reduce my brute force sample rate from 3,000 to 1,000 samples. That's pretty good. So despite the success that we had today, the software is still less than ideal and it's basically just proof of concept. Unfortunately, I don't have the time to do an analysis of the code today, but if you're looking for bonus material, well, there's a segment that was cut out from the main video, and it explains how counts work. This segment was a bit too technical and it slowed down the flow of the video, so it got cut. If you were confused why my data is always in counts and what counts really are, then stick around. If you like this video and want to see more of the stupid simple EFI, then definitely click on the like button, and subscribe if you haven't done so already. We'll see you next time. Until then. So the Arduino, actually any computer, doesn't have the ability to understand analog voltages. You see, a computer like the Arduino only knows ones and zeros, and that's because digital computers only know how to interpret digital signals. Analog signals literally do not compute. So that's a problem engineers figured out a long time ago. A digital 1 is typically 5 volts, and a digital 0 is, well, 0 volts. Any voltage in between 5 and 0 is a mystery to the Arduino. So, if we put an analog voltage on the analog input pin 1, the Arduino can measure it, but it's not in a normal way. You see, despite it not understanding analog voltages, it does have a clever way to measure them. Let's zoom in and take a look. So, this is analog port 1, and this is the ground pin. Now in this example, we're going to put 5 volts across pin 1 and ground and have the Arduino read it. By the way, 5 volts is the maximum voltage that the Arduino can read. If you try to read more than that, you'll damage the circuits inside the Arduino. So when we ask the Arduino to do an analog read, the first thing it does is closes this switch to pass that sample voltage onto this capacitor, and that'll allow the capacitor to charge up to whatever voltage is on analog pin 1. This is oversimplified, and this switch is actually a transistor of sorts. Remember, transistors are basically just electronic switches. Anyway, after a brief amount of time, the capacitor is charged with the sample voltage, and this switch will open. Now here comes the exciting part. This switch will close, and this guy will recognize that the sample voltage is greater than 0 volts. So it'll start counting how long it takes for the voltage to reach 0. The voltage across the capacitor will start bleeding down through this resistor to ground, and while the voltage is greater than 0, the clock will continue to count. At some point, the voltage across the capacitor reaches 0 and the clock stops counting. Now, since we put a full 5 volts across analog pin 1, it took exactly 1023 counts for the sample voltage to reach 0. If we put half that voltage, which is 2.5 volts, it would take 512 counts of the clock to reach 0, and if we sampled 0 volts, it would take 0 counts on the clock. Hopefully that makes sense. Counts are basically how long it takes for the sample voltage to reach 0 volts. The point I'm trying to make is, any analog voltage that gets sampled by the computer, the value will be reported in counts. Now counts is the raw number, and if desired, with a few extra lines of code, we can convert counts into engineering units. In this case, we could use a formula like this. Volts equals counts multiplied by 5 divided by 1023. Of course, that's for voltage. Now, for something like the map sensor, the output of the sensor is going to be an analog voltage, but the map sensor is actually measuring the pressure inside the intake manifold, and in engineering units, we would want to see the data in kilopascals or inches of mercury. A few lines of code will convert the data into whatever you want to see it in, but that requires knowing the calibration data of the sensor to get the exact value. Calibration isn't that hard to do, but a lot of the time I just look at the data in counts and leave it in counts. Leaving it in counts is sloppy, but for now it's fine for what I'm doing. Now the actual time it takes the Arduino to do an analog read is about 100 microseconds. So, in the average blink of an eye, the Arduino can do about 3,000 analog measurements. That's pretty quick, but keep in mind when an analog read is requested, the CPU will halt all other functions until the request is completed. Or in other words, while an analog read is in process, the CPU cannot do other things. There are ways around this with fancy code, but for our project, well, we're okay as far as speed goes.